At this point, we've learned a lot about Laplace transforms, a few of their overall properties, and kind of a pretty sizable list of specific Laplace transforms for the most important formulas. The last piece we need before we get into the application of all this stuff to differential equations is not only are we going to need to be able to take Laplace transforms of functions, but we're going to need to go backward as well. And so that's the inverse Laplace transform. We are going to use the symbol L to the minus 1 to mean inverse Laplace transform. So the idea is if the Laplace transform of our little y is big Y, then the inverse Laplace transform of big Y will be little y. Okay, so it's just like sine and inverse sine, right? They undo each other. They're that kind of a thing. Derivative and antiderivative, that kind of a thing. In fact, that's more of an apt analogy because derivative and antiderivative go between functions, and Laplace transforms and inverse Laplace transforms go between functions. Okay. So, conceptually this is really simple. So we can just turn around all the rules that we've learned, right? So if I tell you that y of s is 1 over s squared, you can look up on your list of Laplace transforms and look under the transform column and find 1 over s squared and find that it is next to t. Okay, that's pretty easy. The inverse Laplace transform has the same two linearity properties that the Laplace transform does. In other words, the two things, you can do the inverse Laplace transform on each part of a sum or difference, and also constant multiples kind of just go along for the ride and they don't affect things. So what do I mean by that? I mean, suppose we have a Laplace transform, a capital Y, that looks like this, 4 over s minus 6 over s cubed. And we want to figure out what the original function was. So we want to take an inverse Laplace transform. Well, 4 over s. Well, we know 1 over s is the Laplace transform of 1. So 4 over s would be the Laplace transform of 4 times 1. So 4. I'll put times 1 here just so it's clear. Now, so this is like 4 times 1 over s, and 1 over s we knew. Now, 6 over s cubed. We look on our table and we know 2 over s cubed. So let's put a 2 over s cubed, right? But of course, we have a 6, so we need a 3 sort of as the extra part that 2 over s cubed does not account for. So 3 times 2 over s cubed. And we know 2 over s cubed is the Laplace transform of t squared. So this would be 3t squared. Okay, so 4 minus 3t squared. That would be the inverse Laplace transform of the capital Y we started with. The only way that this can get much trickier is when your capital Y comes to you in a form that doesn't make it obvious that it matches up with the ones you know. So let me show you an example of that. Well, actually, let me play off of the one that I just showed you. This one's not that bad. 4 over s minus 6 over s cubed. If I get a common denominator here, right, if I write 4s squared over s cubed, right, which is the same as 4 over s, minus 6 over s cubed, right, so 4s, it's common denominator, so 4s squared minus 6 over s cubed. If this is how that capital Y was given, and it really is the same, okay, well then we would have needed to have recognized, oh, okay, I can divide s cubed in here, and here I'll get a 4 over s, and here I'll get 6 over s cubed, and then I know I can work on either of those as we did up there. So there's a real quick example. So if you were given something like this, you would have to first break it up, and then you could identify the pieces that are on our Laplace transform tables, right? And then we could do it that way. But it can get a little bit trickier. Let me show you another one. Suppose this rational function is your Laplace transform. It's your capital Y. Okay, so this one it's not at all obvious what we can do here, like the last one. But the denominator can be factored. That is s plus 1, s minus 4. And then what we're going to do is use a trick that you would have learned in probably a Calc 2 class, which is partial fractions. And it's basically getting a common denominator in reverse. It's breaking this back up into something over s plus 1 plus something over s minus 4. And typically it will just be a number here and a number here. Right? You can imagine that if you pick the right numbers here and here, then this, if you got a common denominator, could turn into this. So this is just going backward. And that's called partial fractions, decomposing it according to partial fractions. At this stage, I think everybody would have learned how to do this in Calc 2. I don't want to reteach the algebra of it, even if it's not fresh in your mind. We can rely on technology for this. So let me just at this point indicate that for the TI calculators, TI-89s and TI-Inspires, at least the CAS versions, if you put this rational function, in fact, better, even go back to the original one, and put it into an expand command. So you can literally type out expand, or you can find the command under a menu. Expand, and then put your formula. It will do this for you. And I think what we find is that it ends up being 7 and a negative 3. This is definitely doable manually, but like I said, I don't want to get bogged down and slowed down by that. It's just a little bit of algebra, and I would like us, in the same way that we often will just use our calculators to do slightly tricky antiderivatives, let's use our calculators or some kind of technology to do these partial fractions decompositions. Nothing deep is going on here. It's a little algebra trick, really. Besides TI calculators, let me just say that also Wolfram Alpha will do this. And I can show you this. You actually type partial fractions, and then you put in the formula. So for us, it would be 4s minus 31 divided by s squared minus 3s minus 4. And here you see it. Let me see. Yeah. Let me just, it's not happening here, but sometimes they'll give you a result here, but sometimes at the bottom they'll give you what they call, I think they call it an expanded form, and that can be more useful. In this case, they're not showing us any expanded form. This is the best version of it. But if you ever see an expanded form down at the bottom of this list, use the expanded form. It's going to be more like what we need. Okay, so there you go. So we should be able to figure out these partial fraction decompositions without too much trouble. Now, why does it help us? Well, okay, now it's in a form that I think we can do something with. We want to recognize these as Laplace transforms of known functions. So the 7 and the minus 3 on top, they are just going to be constant multiples. So this would be like 7 times 1 over s plus 1. Now 1 over s plus 1, if we look on our chart, that would correspond to a Laplace transform of e to the 1t. Right? That's the exponential. So we'll have a 7 times e to the 1t. That's the inverse Laplace transform of that piece. All right, then we'll have, well, it's really a subtraction here, 3 over s minus 4. So that'll be 3 e to the 4t. Okay. And what you'll find is a lot of times these rational functions will break into things that turn out to give you on the inverse Laplace transform side exponentials, or sometimes sines or cosines. So exponentials and sines and cosines will come out of this process a lot. Okay, well, I'll stop this video now because we'll see more examples of this when we start applying this to differential equations.